Hello and welcome to another Toddcast. We're in the midst of alkynes, but we came across something known as an enol. And so want to make sure that this material, although it belongs in the carbonyl section, we have to cover it now, but I want to make sure I keep it separate. So this is actually going to be a really quick one slide and done lesson. But tautomerization is a type of isomerization. So tautomers are isomers of one another, but they're unique in the sense that they are very, very systematic. You either gain or lose a proton to start out with. A pi bond resonates over from one location to another, and then you lose or gain a proton. Meaning, if you added a proton to start, and it resonated over, then you lose a proton. Or if you lose a proton in the start, then it resonates over, and then you add a proton. So long story short, it's just going to be acid base, resonance, acid base. So because of that, we can do this in either acidic conditions or basic conditions. So I want to look at the transfer of electron density first under basic conditions. Under basic conditions, you'll lose an H. So I'm going to try to color coordinate and note which one. But here's my ene, my double bond, carbon-carbon double bond, all with an OH. This is going to be our most acidic proton. H is on carbons, not very acidic. H is on sp2 carbons, even less acidic. H on an O. pK in the neighborhood of 15 when it's in regular alcohol. Because of the resonance coming over here, it's a little bit lower. So let's say it's 10-ish or so, maybe 12-ish, something like that. But with a strong enough base, we can pull that proton off. So I'm going to choose hydroxide, just the easiest one, simple and small. And if it comes in and pulls off this H, we now put a negative on the O associated with what used to be the enol. Now we refer to it as enolate, because again, O's with negatives in a complex molecule or a polyatomic molecule, it's an 8. So we have an enolate. Any of the lone pairs is going to choose the easiest one for proximity, but it's going to come in. So when it comes in, it's going to form a pi bond here. This one's going to move over. So this is a resonance structure, hence the resonance arrows, where we now have a carbonyl and the pair of electrons on this adjacent carbon. It's negative. Now it's simply a matter of picking up an H. Well, base can't give me another H because it's already given off one that's negative. But when I protonated here, I had water, so it's aqueous basic conditions. There's a water in there as well. So this lone pair can then come pluck off an H. When it does that, you end up regenerating the OH minus, and you end up moving what used to be on this O is now on this carbon. So as mentioned in the alkynes lecture, we first came across tautomerization and an enol ketone or an enol aldehyde exchange. That's what we get here. So the H moves from the O to the neighboring carbon. The pi bond moves from between carbons and ends up between carbon and oxygen. Pretty straightforward, but it's common enough. In fact, for anybody who's taken biology, you'll find it as a step towards the end in glycolysis. So in the generation of pyruvate, you actually have an enol to ketone step. Okay, under acidic conditions, so unlike base conditions where we deprotonate, resonate, protonate, we're going to do the opposite. We're going to protonate, resonate, deprotonate. So the first step will be protonation. So I'm going to note this O in red because it's acidic conditions instead of the H in blue for basic conditions. And what's going to happen is we're now going to come and we're going to protonate this alkene. So because of resonance, this can come in here. It puts a partial negative on that carbon right there. So that's going to be our most basic site. So the pi electrons are going to come up here. Those are going to be able to resonate and stabilize it. So when those electrons come up from the pi bond, pick up the H, pushes electron density back to water. So we regenerate neutral water. We've had an H on the site that we need to add one. So I'm going to cheat and look back at this example. We now have a carbocation here, which can be resonance stabilized by that O. There's our resonance. So we go from protonate, resonate, and now simply deprotonate. So I have an O with a positive charge. Simply take that H off. So the water we generated here, or probably not the same molecule, but water we have in solution can come take the H. Those electrons can move back over, and you end up with the carbonyl. So it's not a very elaborate or complicated mechanism, but it's still a mechanism that we have to understand. So again, if it's basic conditions, deprotonate, resonate, protonate. Acidic conditions, protonate, resonate, deprotonate. Guarantee this will pop up repeatedly in carbonyl chemistry. This is going to be a very common reaction. And like I mentioned, biochem's going to have it as well. But this is a one and done. Hopefully this makes it clear. And I'm assuming you're watching this for the first time in the alkyne sequence, but it's also going to show up again in carbonyls. You're probably going to revisit this. Have an absolutely wonderful day, and thanks for being a part of the ever so fun, enjoyable Toddcast series. See you soon. Bye.